Everything you think you know about the center of our galaxy might be wrong. Not slightly wrong. Fundamentally, completely, cosmically wrong. And the evidence is mounting. For decades, we have told ourselves a story. At the heart of the Milky Way, 4 million times more massive than our Sun, sits a supermassive black hole. A monster. An abyss. A point in space where gravity wins so completely that not even light escapes. We named it Sagittarius A star, and we were so confident in its nature that scientists won a Nobel Prize for studying it. We captured what we called its shadow. We watched stars tear around it at a fraction of the speed of light. The case seemed closed. It wasn't. Because here is the thing about black holes. We have never actually seen one. Not truly. What we see are the effects they produce. The distorted light, the whipped orbits, the radio silence at their hearts. And it turns out at least one other thing could produce every single one of those effects with such precision that our best telescopes cannot tell the difference. Something stranger, older, and in many ways far more unsettling. Something that doesn't collapse into a singularity. Something that doesn't trap light behind an event horizon. Something that, if the latest research is correct, has been hiding in plain sight at the very core of our galaxy, and stretching invisibly through it and beyond all along. This is the story of what Sagittarius A star might actually be, and it changes everything. To understand why this matters so deeply, we need to go back to the beginning. Not just the beginning of this discovery, but the beginning of our understanding of the galactic center itself. In 1932, a radio engineer named Karl Jansky was trying to identify sources of interference in transatlantic telephone signals when he detected a persistent hiss coming from the direction of the Sagittarius constellation. The signal didn't move with the Earth's rotation the way the Sun did. It moved with the stars. He had, without quite realizing it, picked up the first whisper from the heart of our galaxy. For decades, that whisper was a mystery. Clouds of gas, clusters of stars, supernova remnants, all were proposed as explanations. It wasn't until 1974 that radio astronomers Bruce Ballack and Robert L. Brown isolated a single, extraordinarily compact source at the galactic center and named it Sagittarius A. And when theorists began applying what they knew about black holes, which by then had transitioned from mathematical curiosity to serious physical prediction, it didn't take long before the simplest explanation seemed almost obvious. What else could pack that much mass into that small a region? By the 1990s, 2 independent teams of astronomers had taken that idea and started building the most compelling case in the history of observational astrophysics. Reinhard Genzel, at the Max Planck Institute for Extraterrestrial Physics, and Andrea Ghez at UCLA spent years patiently tracking the orbits of stars near the galactic center using the world's most powerful infrared telescopes, the Keck Observatory in Hawaii and the Very Large Telescope in Chile. What they found was extraordinary. A cluster of stars, now called the S stars, was locked in tight, highly elliptical orbits around an apparently empty region of space, moving at speeds that were almost impossible to comprehend. One of them, designated S2, completes a full orbit in just 16 years. 16 years. Our own Sun takes more than 225 million years to make the same trip around the galaxy. S2 reaches a peak speed of around 7,650 kilometers per second during its closest approach, nearly 3% of the speed of light. Another star, S4716, was later identified, completing its orbit in just over 4 years. These are not gentle paths. They are the trajectories of objects under the influence of something almost incomprehensibly massive and almost incomprehensibly small. The central object weighs in at approximately 4.3 million solar masses and is confined to a region roughly 25 million kilometers across, small enough to fit comfortably inside the orbit of Venus around our Sun. In 2020, Genzel and Gaze were awarded the Nobel Prize in Physics for this discovery. But look carefully at the official citation. It does not say they discovered a black hole. It says they discovered a supermassive compact object at the center of our galaxy. That phrasing is not accidental. It is a reflection of a scientific truth that tends to get lost in the headlines. We have never proven that Sagittarius A star is a black hole. We have proven it is massive. We have proven it is compact. But those two things alone do not a black hole make. And this is where the story takes its radical turn. In February 2026, astrophysicist Valentina Crespi at the Institute of Astrophysics La Plata in Buenos Aires published a study in the monthly notices of the Royal Astronomical Society that sent a quiet but seismic ripple through the physics community. Her question was precise and pointed. Could a dense core of dark matter reproduce the observed orbital behavior of the S stars and the enigmatic G objects with the same accuracy as the supermassive black hole model? The G objects are strange things. Discovered in the early 2000s, they appear to behave simultaneously like stars and gas clouds, stretching and distorting as they swing close to Sagittarius A star, responding to its gravitational field in ways that shift their visible shape. Any alternative model for Sagittarius A star would have to reproduce this complex behavior precisely. It could not just match the orbits of stars in a rough, approximate way. It would need to work at the level of fine observational detail, because the data on S2 and the G objects is among the most carefully gathered in all of astronomy. Crespi's results were remarkable. The dark matter core model reproduced the observed orbits of both S2 and the 5 known G objects with less than 1% deviation from the black hole model. 1%. That is not a fringe theory scraping together approximate agreement. That is a competing model matching observational reality with the same statistical power as the standard picture. The conclusion was stark. With the data currently available, you cannot tell Sagittarius A star apart from a dense dark matter core. Gravitationally, they are identical twins. But what kind of dark matter are we talking about? Because dark matter is not a single thing. It is a name for our ignorance. We know something invisible and non-luminous provides the extra gravitational mass needed to explain how galaxies rotate, how galaxy clusters hold together, and how the large-scale structure of the universe formed. It comprises roughly 85% of all matter in the cosmos. And yet, we have never directly detected a single dark matter particle. Not one. Despite decades of increasingly sensitive experiments, it remains the most abundant and least understood substance in existence. Crespi and her collaborators, including astrophysicist Carlos R. Argüelles, the group leader at La Plata, are not proposing just any dark matter. They are proposing dark fermions. This idea has a longer history than it might seem. In 1969, Ruffini and Bonazzola first explored the idea that fermionic particles could form gravitationally bound quantum objects of significant mass. The concept has persisted at the edges of the theoretical literature ever since, occasionally surfacing, occasionally being refined, never quite going away, because the physics underlying it is genuinely compelling. Fermions are a class of subatomic particles that includes electrons and quarks, the fundamental building blocks of ordinary matter. What makes them distinctive is that they obey the Pauli exclusion principle, one of the deepest rules in quantum mechanics. No two identical fermions can occupy the same quantum state simultaneously. They cannot be stacked into the same location with the same energy and the same spin. This is not a suggestion. It is a quantum law. And it is the reason matter has structure, why atoms do not collapse, why solid objects resist compression, why you cannot push your hand through a table. Dark fermions are proposed to be elementary particles that share this fermionic nature, but interact with ordinary matter only through gravity. No electromagnetic interaction. No light emitted, absorbed, or reflected. Completely invisible to every detector we build except through their gravitational influence. Because of the Pauli exclusion principle, dark fermions would resist being squeezed beyond a certain limit. They would push back. They would build up quantum pressure. And, under the right conditions, enormous quantities of them collapsing together across cosmic timescales. This pressure could stabilize into an ultra-dense, compact, gravitationally massive object. One that reaches the mass of millions of suns. One that occupies a region of space small enough to fit inside our inner solar system. One that, in every gravitational sense we can currently measure, looks exactly like a supermassive black hole. Except it would have no singularity, no event horizon, no point of no return. At its surface, light would bend violently, but it would bend and escape, rather than crossing a threshold from which it can never return. The interior would be a dense quantum object, not an infinite gravitational collapse. And here is where the model becomes something far more than just an alternative for Sagittarius A star. Because dark fermions would not stop at the galactic core. The same physics that allows them to form a compact central object would also govern their behavior throughout the galaxy and beyond. They would form a halo, a vast, diffuse, roughly spherical distribution stretching far beyond the visible disk of stars and gas. Not as a separate structure, not as a coincidence. As the natural outer continuation of the same fermionic dark matter field that forms the dense core at the center. This is what makes the La Plata model so intellectually striking. Every other theory about Sagittarius. A star treats the compact central object and the galactic dark matter halo as two entirely separate things, two different structures that happen to coexist. The fermionic dark matter model is the only hypothesis that unifies them. The galactic center and the galactic halo are not two problems with two answers. They are two manifestations of a single, continuous structure, a fermionic dark matter distribution that is simultaneously ultra-dense at its core and diffuse at its edges. This unification has observational consequences. ESA's Gaia mission, which has been measuring the positions and velocities of nearly 2 billion stars across the Milky Way with extraordinary precision, published results in 2022 that revealed something unexpected at the outer edges of the galaxy. The rotation speed of stars in the outer disk drops off, a phenomenon called Keplerian decline. This was a problem. Most standard dark matter models predict that rotation speeds in the outer galaxy should remain approximately flat, supported by the extended dark matter halo. But Gaia showed a fall-off. The outer disk is slowing down in a way the standard picture struggles to explain. Fermionic dark matter offers a natural solution. Because dark fermions obey the Pauli exclusion principle, the halo they form has a physical edge, a defined boundary where the fermionic pressure that holds the structure together gives way to the surrounding emptiness of intergalactic space. This creates a sharper drop-off in mass density at the halo's outer boundary than standard dark matter models predict. And that sharper boundary produces exactly the kind of Keplerian decline that Gaia observed. The galaxy is not just rotating, it is tracing the shape of its own dark matter halo, and that halo has an edge. Then there is the shadow. In 2022, the Event Horizon Telescope collaboration published the first image of Sagittarius A star. It was a triumph of global scientific cooperation. 8 radio observatories across 4 continents linked together to form a virtual telescope the size of Earth, capturing light at millimeter wavelengths that could pierce the dense interstellar dust between us and the galactic center. The image showed a glowing ring of superheated plasma, bent into a circle by the extreme gravity of Sagittarius A star, surrounding a central dark region. That dark region was widely described as the shadow of a black hole. But what is a shadow precisely in this context? It is a region where the gravity of the central object is so intense that any light falling into it cannot escape back toward us. For a black hole, this is the event horizon doing its work, the point of no return capturing photons that stray too close. For a dark matter core, the same visual effect can be produced if the central object is dense enough that light bending around it creates an equivalent dark central region. In a 2024 paper, Arguelles and his collaborators demonstrated mathematically that a fermionic dark matter core of the appropriate mass and density would bend light so strongly that it would produce a central shadow of almost identical angular size to the one seen in the EHT image, indistinguishable from a black hole shadow with current instrumentation. As Crespi has noted directly, the model is consistent with the EHT image. The dense dark matter core mimics the shadow because it curves space-time around it just as powerfully. The ring of light is bent. The center appears dark. The picture looks the same. Our most celebrated image of the galactic center does not, by itself, prove there is a black hole there. There is another dimension to this story that reaches far beyond the Milky Way. The James Webb Space Telescope has been transforming our understanding of the early universe since it began operations in 2022. One of its most puzzling discoveries has been a population of extremely compact, extremely massive objects in the distant universe, compact enough and red enough to earn the nickname Little Red Dots. These objects appear to have masses of hundreds of millions to billions of solar masses, and they exist at redshifts corresponding to less than 1 billion years after the Big Bang. The question they pose is almost existential for standard cosmology. How did objects this massive form so quickly? Supermassive black holes require time and a sequence of events, seed black holes forming from massive stars, or dense stellar clusters, growing through accretion, merging, growing again. Getting from a stellar remnant to 1 billion solar masses in under 1 billion years is extraordinarily difficult under current models. Fermionic dark matter cores face no such bottleneck. In the dense, hot conditions of the early universe, dark fermions would have been able to clump directly into gravitationally bound configurations, without needing stars, without needing prior black holes, without needing any of the intermediate steps. They could form quickly, grow to enormous masses, and sit at the centers of their nascent galaxies from very early cosmic times. The little red dots in this picture are not a mystery. They are what the cores of the earliest galaxies look like. Now it is essential to be clear about something. The fermionic dark matter hypothesis has not overturned the consensus. It has not been proven. And Crespi, Arguelles, and their collaborators are explicit about this in their published work. The current observational evidence, the S-star orbits, the G-object behavior, the Gaia rotation curves, the EHT shadow, is consistent with both models. What their work has demonstrated is that the dark matter core model cannot be ruled out by the data we have. That is a significant and meaningful scientific result. It keeps the question genuinely open. What would settle it? The answer lies in a phenomenon unique to true black holes. Near a real event horizon, the extreme curvature of spacetime forces photons into extraordinary behavior, spiraling in tightly curved paths before falling beyond the horizon forever. These spiral paths can produce distinct structures called photon rings, faint, nested rings of light sitting just outside the black hole shadow. A dark matter core, lacking an event horizon, would not produce these photon ring signatures because there is no ultimate gravitational trap forcing light into those extreme orbits. Light bends, but it escapes. The photon rings simply do not form. Imaging photon rings around Sagittarius, a star, is an active observational goal. NASA's proposed Black Hole Explorer mission is designed to place a radio telescope in space and link it with next-generation ground-based arrays, creating a virtual telescope significantly larger than Earth, with angular resolution capable of resolving structures far finer than the current EHT. The timeline for such a mission stretches into the 2030s and beyond. In the meantime, the Gravity Plus Interferometer at ESO's Very Large Telescope Interferometer in Chile is already measuring the pericenter precession of S2's orbit, the subtle rotation of its closest approach point with each pass around Sagittarius A star. The precise direction and magnitude of this precession encodes information about the mass distribution at the galactic center and could help constrain which model fits best. Simultaneously, direct detection experiments searching for dark fermion signatures, including efforts to measure minute energy depositions from low-mass dark matter particles interacting with atomic electrons, are growing in sensitivity with each new generation of instruments. The deeper you look at this story, the more remarkable it becomes. For generations of scientists, two of the grandest unsolved problems in physics have been treated as entirely separate puzzles. What is the mysterious compact object at the heart of the Milky Way, and what is the invisible substance that makes up most of the matter in the universe? They sat in different papers, different conferences, different corners of the cosmological map. The La Plata group is proposing they are the same problem wearing two different faces. The galactic center and the dark matter question are not separate mysteries. They are one mystery, and the answer, if this model is correct, has been sitting at the heart of our galaxy for as long as the galaxy itself has existed. Is Sagittarius a star, a black hole? Possibly. Probably, if you follow the consensus, but probably has never been the same thing as certainly. And science has a long memory for the times when the consensus was confident. The evidence seemed overwhelming, and the answer turned out to be something no one expected. We are living in one of those moments. The instruments are getting sharper, the data is getting richer. And the question at the center of our galaxy, the oldest question our galaxy has been hiding, is finally being asked with enough precision to matter.